Hello and welcome to another lecture on ECEN 215. Today we're going to talk about RL transients. So this is another lecture in the series on transient circuit analysis. We started with RC transients. We talked about steady state circuit analysis in the DC as applies to transients. And now we're going to finish up with RL transients. So again, what is a transient? A transient is a temporary oscillation and occurs when you apply a sudden change of voltage or load to a circuit. Here we have, where its circuits, there's a voltage of 0, and then we automatically apply this 6 volts to a circuit that has inductive and capacitive loads of various kinds, and it causes this oscillatory behavior, or it could cause an exponential increase or decay of various kinds. In this case, it's exponentially increasing and then decreasing, and oscillatory in the case of this one. And eventually goes to steady state as time increases towards infinity. In this case, just after a handful of seconds, it finally settles out to a steady 6 volts DC. Hence the point of doing steady state circuit analysis. So here we're going to study what if we place an inductor in the circuit instead of a capacitor. Earlier we looked in the RC transients where we had a power supply, a simple power supply like this. We had a switch, we had a resistor, but instead we have a capacitor here instead of this inductor. So it's very similar in nature, and in this case it's just going to act a little differently. In fact, it's going to have a very similar reaction, but the circuit analysis is slightly bit different because if we remember, inductors work off of current, and they prefer to have a constant flow of energy, constant current, because the energy in the case of inductor is stored in the magnetic field versus in a capacitor, the energy is stored in the electric field. So here, the inductor is wanting to maintain the magnetic field going through it and wants to do that, and as the current is changed, it alters the voltage across the inductor. So this, if you can kind of imagine here, we got this I of t going through the circuit, and we're going to apply an analysis to determine what V of t is across the inductor. So let's start that analysis process. So here we have our circuit. We have, in this case, 100 volt power supply is Vs. We have t is equal to 0, meaning that at time 0, the switch is thrown in the circuit is just simply a 50 ohm resistor in series with this inductor in series with this power supply. Prior to time is equal to 0, the switch is disengaged, which means the circuit really is just simply this power supply. So let's first do some circuit analysis of the circuit once the switch is closed. By doing that, we're going to use mesh current analysis instead of nodal voltage method. The reason why is we're using this I of t as this nice loop current, and we can simply just apply the voltages across the different elements, sum them up. It becomes a much easier analysis because of the nature of the inductor. So let's do that. So in this time, instead of writing KCL equation, we're going to be writing the KVL, the Kirchhoff's voltage law equation. So the loop, what Kirchhoff's voltage law says is this loop must equal 0, all the voltages added together, starting here in the voltage across the resistor, the voltage across the inductor, and then the voltage coming in the negative terminal, subtracting V of S must equal 0. So let's go ahead and write those values. So R times I of t plus VL, basically the voltage across the inductor, VL of t, whatever that is, minus Vs. This is our governing equation for this circuit. That must be followed. Now we do know an equation for VL of t. VL of t is equal to L di dt. So the current going through the inductor, IL dt times the inductance value, in this case 0.1 henries, is equal to the voltage drop. So we just simply replace this. If we know what I of t is, then we now have a differential equation that we can go through and solve. So let's go ahead and do that. Let's go ahead and apply this process to the circuit. So there's our equation. Similarly, we have everything very similar to what we had with the RC circuit, but now everything is in terms of I of t instead of V of t. So we have a differential equation, so now let's look for a solution. This solution looks suspiciously like the solution we had before, because it is. Again, and this is, you can see why we did KVL instead of KCL. because this solution, instead of now being in voltage, is now in terms of current, is exactly the same solution, K1 plus K2 e to the st. So again, we now need to go through and solve for K1, K2, and S to get a solution for this circuit. So first of all, we can go through here and taking a look at this. If we take the derivative of both sides, take di dt, we end up with K2 e to the st. And we end up with this right here to solve for. And now we have everything in terms of L and K, so on and so forth. We just basically replace all of this with this equation. We start with I is equal to this. The derivative is K2 EST. Plug this all into this equation, and we end up with this. And we just need to go through and start solving for things. So again, regardless of the scenario, this equation must in the end become Vs. So let's kind of reduce things a little bit here. We end up with R K1 plus e to the st, so we can factor out the e to the st, times this constant K2R plus K2SL. Must be equal to Vs. So we're going to solve for K1 first. So we do that, we come here, and we're just going to assume for the moment, because K2 can be, again, the constants can be anything. So if K2 happens to be 0, that would completely get rid of this term, and we end up with R K1 is equal to Vs. So simply Vs is equal to Vs over R. So that's our constant K1. So if we're going to, we put that aside for a moment. Now let's go through and solve for S. So again, this is, we're solving for S. We're going to have this, and we go through. We end up with R plus S is L must be equal to 0 for that to occur on this side of the equation. So if we do that, we end up with S is equal minus R over L. Again, this is your effectively similar to your time constant. Your time constant here is going to be L over R. So we end up, and now we have replaced K1 and S in the current equation. We end up with this. So I of t is equal to Vs over R plus K2 e to the minus R over LT. And now we need to solve for K2. So we know at time is equal to 0 minus, or right at 0, the current going through the initial is the current going through the initial, the initial current going through the inductor. In this, so of I is 0 minus is equal to Vs over R plus K2S RL over 0. So right here, if that's 0, again, this term becomes 1 because you're raising the exponential to a 0, which becomes a 1. You have Vs over R. So whatever the initial current is going through this inductor, and in every problem, they're going to tell you, in the case of the capacitors, assume the initial voltage is 0, or they're going to give you some initial voltage, or they're going to give you an initial current. So that's going to be what this is. So if it's 0, then that becomes pretty easy to solve. And if it's actually a known value like 2 amps, you can solve for this. And we're just solving for K2. Again, this is Vs over R plus K2 because this right here is a 1. And so all we have to do is solve for K2, where this is the initial current. If initial current was 0, then K2 is minus Vs over R. So this is an important thing to kind of look out for if you are following this formula here, and you've got K, we already got K1, and we have S, and we're just solving for K2. K2 may change if the initial current is something other than 0. So if it is initial 0, then we just end up with K2 is equal to minus Vs over R. Now we replace K2 in the current equation, and we end up with this I of t, which is the current going through the inductor, and throughout this entire circuit is Vs over R, which just happens to be the current going through this resistor here, kind of the steady state current, if you will, because now it's considered this inductor shorted, minus Vs over R, e to the minus R over LT. So we replace that in our KVL equation, and now we end up with Vs is equal to S. Everything seems to balance, and that we know we have the correct solution for I of t, because if we do that for time 0, everything appears to be correct. So what does that look like? We have here at 2 milliseconds at tau, we have 1 point for a 2 amp Vs over R. In other words, we're going to go up to 2 amps total. We end up with 1.264 amps at 2 milliseconds. Kind of the same as before, 63.2% of 2 amps happens at the time constant. Very similar to the RC circuit, it's just instead of now looking at the voltage, we're looking at the current. And then, of course, the voltage across the inductor as time goes on initially is equal to Vs. So the switch trips and the voltage across the inductor is equal to, at that very instant, is equal to the voltage on the power supply. And then because the inductor immediately is going to try to resist the change of the current going through it. In other words, it was wanting 0 amps going through it. That's what it had initially. And now you're going to put current through me. I don't want that as an inductor, so I'm going to apply an equal and opposite force, but it will eventually decay over time. And this is exponential, and it's going to be V of t. It's going to go from 100 volts, and it eventually will decay to 0. Now, in a similar vein that we had with the RC circuits, we have this much more complicated circuit where we have this 100 ohm resistor that is that's being switched in and out. We have this 100 ohm resistor here that's in series with the inductor. What do we do here? Well, again, we're looking at the initial current, and we have remember that K2 factor that we had a moment ago? That's what this is going to apply here. So here the circuit's a little more complicated. What we're going to do is we're going to change the current as time is equal to 0. So there's going to be, at time is equal to 0, this switch goes from shorting out this resistor to basically adding in, instead of 100 ohm resistance, it's going to be 200 ohm resistance. So at time is equal to 0, this circuit becomes a 100 volt power supply, 200 ohms total here, and an inductor. And prior to time is equal to 0, so time way less than 0, we can do a steady state circuit analysis and assume that this circuit's been sitting in this state with this switch not connected for a long period of time. And so what happens in a steady state circuit analysis? This is a short. So you just have 100 volts with 100 ohms only going through it. So you have 1 amp that's constantly flowing through this circuit. Way less than 0. So at time, say minus 10 seconds or something, or 2 minutes or 100 minutes, there's only 1 amp because during that DC circuit steady state analysis, this is a short. So it's simply a 100 volt power supply. This switch is closed at time prior to 0. So this is a short, and it's just a 100 ohm resistor. So you have 100 volts and 100 ohms. It's 1 amp is the initial current going through the inductor. And then when we open the switch, then we end up with a 200 ohm circuit and an inductor. So following through, we end up with that K2 factor as initial current. In this case, it's 1 amp because of the initial circuit. So you end up with 1 amp minus Vs over R. Well, in this case, Vs over R is the circuit configuration at time is equal to 0. So R is now going to be 200 ohms. So this here would be 1 amp minus 100 volts divided by 200 ohms, which is now half an amp. So K2 is going to be 1 minus a half, or a half. So if you were to ask the equation, what is I of t for this particular circuit here, we end up with Vs over R, which is a half an amp, plus, because it's 200 ohms in total after t is equal to 0, so we've got Vs equal to 100 divided by 200, so 1/2, plus, in this case, 1 minus a half, or half, so again a half, e to the minus RL over t. So you end up with a half an amp plus and a half an amp that is going to eventually decay up. So in this presentation, we discussed transients, and specifically we discussed resistor inductor circuits, RL circuits, and their behavior based upon an instantaneous change of voltage or current being applied to the circuit, transient behavior. Um, if you need more information or have some questions regarding that, which would be understandable, these are more complicated problems than what we have been introduced to so far in this class, and we're actually using some advanced differential equations and things, and so you might be the first time that you're seeing this in your studies here at Texas A&M. So please come by the Q&A lectures and we can discuss this more in detail, or of course obviously come by the office hours if you need anything specific. So have a wonderful day.